Okay, good afternoon, everybody. It gives me a great pleasure to introduce our speaker today, Selma de Mink. Selma did her PhD at Utrecht. She got her PhD in 2010, and then from there moved to the US. She was a Hubble Fellow at the Space Telescope Science Institute and Johns Hopkins from 2010 until 13. And then she moved on from there as a Einstein Fellow and a Lyman Spitzer Fellow to the Carnegie Observatories and Princeton Universities, but she only stayed for a year before going back to the Netherlands to join the faculty at the University of Amsterdam, where she started about 8 months ago or so, 6 months. So Selma has done a lot of work on massive stars, the role of rotation and binarity, and that's what she's going to tell us about today, the complicated lives of massive stars.
Thank you very much. Thank you very much for having me. I stayed for 2 weeks. Has been exhausting. I think I talked to almost 30 people. So if I have slightly less energy than you saw me earlier this week, then I apologize, but I'll try to deliver this. I'm passionate for this topic. This is stellar evolution. As I said earlier, for some people this is a field that was solved half a century ago, right? And so on the computational side, we improved a little bit on computer speed, which is nice. We can do a few more stars per hour now on our computers, but a real understanding of how to do this has been very hard. We still model these things in one dimension, mostly, apart from a few processes. The real progress here has been coming from observations. So I'm on the theory side, but I work closely with observers. And so I think some of the most exciting developments you already see on my title slide. So in the background you see a star cluster, R136. And so in the center, just falling off the screen, that's the center of the cluster. And there's claims now that stars have masses of, birth masses of 300 solar masses. So I don't know if that sounds high to you, but probably you used 120 solar masses as an upper limit. Maybe if you ever thought stellar evolution, you can make a very simple derivation. And if you do it too simplified, you get an upper mass limit around 100 solar masses. That's probably because you didn't put the right scaling in. But so from the theory side, there is no fundamental upper mass limit. If you tell me to make a star of 1 million solar masses and solve the equations of stellar structure, that is possible. That we find a stable solution. Just such a thing would be so bright and have such a wind that it would maybe not exist very long. But so we didn't know how massive stars were. This is results from the last few years. So that's not directly my work, but we're trying to understand these stars. So there's crazy things going on. And so that's the type of things I will talk about today. These are the students I have in Amsterdam that are teaching me stellar evolution now, and it's really great to work with them. For my talk, I should acknowledge quite a few collaborators that inspired different parts of this. Maybe they don't agree with all I say, but that's a different story. Especially many of the Tarantula Survey Massive Star Consortium, and 2 people in specifically, Hugues Sana, one of the observers I work with, and Rob Izzard, one of the modelers I work with. So let's motivate. Why shall we talk about massive stars? Well, the models of massive stars are widely applied in many fields of astrophysics, and you might not be fully aware of it sometimes that you're using it. But this is because massive stars have many roles in astrophysics, and we could sort of divide this in an active role and a passive role. So in the active role, we think of them as cosmic engines. And in the passive role, it's the cosmic probes. And so the cosmic engines, I'm thinking of how did they transform the universe starting from the formation of the first stars, which were supposedly very massive. How did they make the universe transparent? How started they to make the first elements, the oxygen we breathe today? How did they transform it into the universe in which we live today? And the cosmic probe side, we use these massive stars to study the most distant galaxies we have. The light there from the star-forming galaxies is from these massive stars, and if you want to interpret it, you're using stellar models, or the output of stellar models. And so it's important when you think about tracing cosmic star formation history throughout the universe. It's important if you think about the most extreme transients. So this is massive stars exploding at redshift 3.9 and maybe even 8 or 9 for the gamma ray burst. And the end products, of course, are probes for extreme physics of black holes and magnetars and gravitational waves. Who knows, in 2 years we have a detection of gravitational waves. So, what do we know about massive stars? This is the story we teach to our students. This is very simple. This is the story of a star in isolation. A single star, non-rotating, no magnetic field. This is a bit like your high school physics where a cart is rolling down a slope without friction. I've never understood how wheels would work in that case. But this is the story we talk about. There's many phases which are complicated enough already in this picture. So as a rhetorical question, which of these phases depicted here would be the simplest phase? I always like to ask this question. There's two answers I typically get. Anyone wants to throw? So all the theoretical institutes I come, people claim black hole, but what I'm hoping for is main sequence star. That's where I want to go. So at the main sequence, a star is pretty well described by just 4 equations. It's pretty spherical, so you can do it in 1 dimension. And the composition of the star throughout the star is, at the start, pretty constant. And so this is should be one of the simplest phases to do. So let's have a look how well we get the main sequence of massive stars in Hertzsprung-Russell diagram, luminosity, effective temperature. You would hope we get it right here. These are the standard tracks. These are a little bit outdated according to the massive star community, but these are the ones that you probably use if you use Starburst 99. I'm just saying. So this is the theoretical main sequence. This is where stars are supposed to spend all their lives because they're hydrogen burning. And at the end of their life, or when they're done, maybe I need a pointer here. There we go. It's hard to operate 2 things at the same time. Yes. Okay. So at the end here, they leave the main sequence and they start hydrogen shell burning and they accelerate to this direction. So the prediction here is that for each star on this side, there should be around 100 to 1,000 stars in this band. It should be really nicely, thickly populated. I simplified it right a bit, but there should be a really sharp edge here. So let me show you what the observations, some of the recent surveys show. It's nicely populated, but it doesn't behave at all according to the models. And just to point out, to stress again, for each of these guys here, there should be 100 to 1,000 inside this blue bar. There should be a really sharp cutoff if you believe these models. And so that's clearly not there. And so there's different things that go wrong. So on this side, these stars, we call them blue supergiants. And it's very puzzling what they are. On this side, we also have trouble. These stars, in principle, they lie where they are allowed to lie. But according to the models, this would be such a young star, it should be really embedded. So it's very strange we already see it. So there's also discrepancies up here. These blue supergiants, this is really embarrassing case, I think. We don't know what they are. We don't know if maybe these guys are belonging to the main sequence and they're still hydrogen burning. We just did not get this boundary right. That's one option, hydrogen burning. Second option, these models, they go to this side and they come back. I took that out, but it's possible that they're actually helium-burning stars and that they're lying there. But it's, in either way, the models can do that, but they always would have a gap here. You can shift this gap to the left or the right, but it's not going to disappear in your single-stellar models. And so a third option, it's better to show in this diagram, which has data, older data, which is the quality of this data is slightly less, but this is the first time this problem has been pointing out. Here it's really striking, right? This is the main sequence. This is all these stars. A little bit of this problem went away because the spectra of these stars were better. So here in the middle, one of these blue supergiants is a famous one. It happens to be a nearby supernova, 87. That is the progenitor of 87A. So these stars could be on the main sequence early in their life. They could be mature and being helium burning, or these could explode any moment. And we don't know. And it might be a mix of them. So this is the state of the art for main sequence stars on the high mass end of this diagram. And to be honest, this is not really the high mass end. We're talking about 2040 solar masses there. This is the real part where, to be honest, we have no clue what's really going on there. And so that's really the part I'm most interested in, and that's the part where the data, as we speak, we have starting to have surveys there, and first time we start to populate this area. And so the theme I'm really interested in, how does, so these are the classical models, how do these classical models change if you think about rotation, binarity, mergers, possibly magnetic fields. I will not say too much about that, but anything that's more complicated than our standard models. Okay, observations. And this is the same region as on my title slide. This is 30 doradus. This is sort of the Hubble deep field for stellar physics. This has been measured and observed by Chandra for 2 megaseconds. In the background you see a Hubble image. We have 4 or 5 colors in this image. One is the largest mosaics that HST made. And so on top of that, the collaboration I work with, the VLT Flames collaboration, we took for 1,000 bright objects in this region, we took spectra. Not once, but at least 6 times. And it turns out to be at least 800 early type stars. For 800 early type stars, we have spectra at multiple epochs. This is for the first time we have such a large and homogeneous survey, and we can start to populate these diagrams and try to understand it. So this is in progress, and I'll show you results as far as we got so far, but much more will come out. And so this is the exciting region I already told you. In the center, we have the star cluster there, R136. So it has these very massive stars. And the other finding is that actually the star cluster may actually be 2 star clusters that are on the verge of merging. That's one of the things that came out of the Hubble images when we take the first author is Elena Sabi. So we're trying to find out if these stars are really 300 solar masses when they were born. At the moment, we're the group of Paul Crowther, one of our collaborators, is looking at STIS spectroscopy, so HST spectroscopy, that you can go much more detail. But whatever we think of, we can bring these masses down, but it's very hard to bring them back down to 120 solar masses. So this is very worrying because there's 4 stars like that out there. And these 4 stars, I don't know the exact numbers anymore, but these 4 stars have such a significant impact on the UV budget and the ionizing budget of this cluster. If you were thinking about a galaxy in the early universe, and you think about stellar populations, if you don't get these top stars right, you just miss all your ionizing flux, for example. So that's the 2 star clusters. So this region is great. It's breaking any records. And so one of the first records we found in our spectroscopic data set was the fastest rotating star. Measures depends a little bit in what units. Of course, millisecond pulsars will be faster. This is the fastest in terms of the speed at the equator in kilometers a second. And so this one, actually it's the second fastest we know now, but they're very close. Within error bars, there's a second one like this. This one is rotating at around almost 600 kilometers a second. Maybe 550 will be a bit safer. 550 kilometers a second for a star like this is so close that the material at the equator is close to not being fully bound, close to what we call breakup. Breakup is a bad way to refer to this because the star is not breaking up, but the thermal motions of atoms at the equator would be enough to launch them in the disk. And so this is what we think that BE stars are. This is not a BE star, but an OE star. We find several of those. And this one we're very excited about. It was not just a rapidly rotating star, it also has a runaway velocity. It's actually moving towards us, I believe, at 30 kilometers a second. So it's not so fast, but it's at least 3 sigma faster than what you see in the field here. So why would a star be running fast so rapidly? There's another record in this. This is actually a supernova remnant. There's a pulsar here, and that's the most energetic young pulsar, and it's very close. In this paper, we thought they might be connected. There's actually in X-rays you see sort of a finger pointing from one to the other. So what's the chance of breaking a record twice in such a region and having an apparent link between the two? We don't believe the connection between these two anymore, but we do think that this one was a companion, is a secondary star of a binary system that got an injection. Probably not of this one, because this one is just outside the supernova remnant, and that's a bit tricky. What else do we have? Oh yeah, in the top corner there is another record holder, a runaway star of 80 solar masses. It's hard to kick a star of 80 solar masses. So this is probably a different type of runaway star. This is probably a runaway star that was ejected by the central star cluster, not because its companion went supernova, but because probably 3 stars, possibly even 4, but probably 3 stars had a very close encounter, and then probably the least massive of the 3 was shut out. The least massive. This one is 80 solar masses. Well, so that is in line with very massive beasts being in there. So in the background, you see an HST image that we took. There's a second epoch being analyzed at the moment. If this one is really coming from R136, from the central star cluster, we know it's a runaway star, but we only have the spectral velocity to the line of sight. We really want the velocity in the plane of the image. And so we hope to get that very soon, and that will say where that came from there. So that I find very exciting. What else did we have? So it's full of massive binaries, lots of them. Of the of the 800 stars, 300 are the most massive O-type stars. 300 O-type stars, 100 are binaries, 1/3 detected. And so there's probably more binaries. But of the 100 binaries, we have 10 that are contact binaries. And some of these are really crazy. This is in particular one. There's another one, a paper that was just submitted by Almeida et al. 2 contact systems of around 40 or 50 solar masses in contact. So they will merge and make also around an 80 solar mass star somewhere soon. Okay, so it's great to break records, especially if you like to have a press release for your work. But the real thing we learn about is the boring normal stars and what is the distribution of the general properties, right? It's great if you have an extreme rapidly rotator because it's probing the physics of rotation at the extreme end. But to be honest, we want to understand the normal stars first. And so you have distributions of the rotations, information about the binaries, information about proper motions. And there's many more things, but this is the things I will mainly talk about. Yeah, so for the next part of my talk, I'll talk first about rotation, then about binarities, and then how these two things to come together. Yeah. So rotation. This is the same image, of course. This is the press release image. This is the artist impression of this rapid rotator. And for some reason, these stars always need a planet. Which is not, it's not impossible. It has been hypothesized that in this disk, under some circumstances, maybe not for this one, but under some circumstances, you can actually create instabilities that might lead to either star formation or very low mass object formation. So it's exciting to think about. But if it was an old planet, it's going to be hard to still be there because this is now a runaway star. It should have taken it away. So we tried to get it out, but they still wanted it. Good, rotation. This is work by Philip Dufton and one of our students in Amsterdam, Oscar, who's already about to finish his PhD. He has been analyzing all the bright stars. He's been analyzing the O-type stars. So I'm showing you what is the rotation rates of the stars of which we think they're single. Actually, we don't think they're single. We just don't see evidence for a companion. And we don't see evidence of a companion in the variations of the spectra. We don't see radial velocity variations. So for the B-type stars, just to guide your eye, the stars between 8 and 16 solar masses roughly. And the O-type stars, 16 to 60 solar masses. These are the rotation rates. And they span all the way from either non-rotating or stars that we see pole on. Yeah? It's the projected rotation rate. The chance to see a star pole on is not so high. So most of these are pretty slow rotators, up to almost 500 for the B-type stars and over 600 for the O-type stars. So one of these two is the record holder that we found. So these structures are very different. We don't know what to do with that. So what is very intriguing, these results are 20 of these 200, this is 200 stars, 20 of them are runaway stars. Both of these are runaway stars and quite a few of these, a couple slow ones. And so if you look at this, the first question, well, I have two questions, I don't know, maybe you have other questions, but what caused this? What is the underlying physics that sets this? And this has usually been interpreted as a signature of star formation. So if you see this bimodality in rotation rates, should we be thinking about two modes of star formation? And the other possibility is that part of this is not the nature of the stars, but the evolution they undergo. Especially these runaway stars that seems to indicate that it's not their birth rotation rate, but things happened. And so the second question, at least I have, is, well, these velocities are crazy high, these rotation rates. That's not non-rotating stars anymore. What does it do to the evolution of a star? So I'm going to address these two questions in the opposite order. So let's first talk about the consequences of rotation. So we stay with single stars for the moment, and the rotating stellar models. So let's get back to an HR diagram and look at stellar evolutionary tracks. So these are tracks of slow rotators. This is very close to what you probably would see in your stellar evolution textbook, if you still have one. It's only a little bit lower metallicity. And so all stars starts on the 0-H main sequence, if they manage to form. Apparently they do. And they're hydrogen rich. And over time, we know they expand and become bigger because the core contracts and become helium rich and the envelope swells up. And these stars become red supergiants. And this is, at low metallicity, even a 60 solar mass star should be doing that. So this is the slow rotators. So let's look at the rapid rotators. And so if stars rotate, there's many things that change the evolution. So massive stars have interiors where the center is convective and nicely mixed, and the envelope is radiative. Material is not transported. You will not see the elements that are in the center at the surface. That's not happening. If you have rotation, things can change. Suddenly, in this radiative layer, you have ways to start mixing elements from deep inside to the surface. And there's two ways to do that. One is the Eddington-Sweet circulation. It's basically an effect of the star is rotating. It's slightly flattened, which means that there is a thermal imbalance between the poles and the equators, which drives these large-scale flows, the Eddington-Sweet circulation or meridional circulations. And there's another type of mixing that can occur. As stars rotate when they're born and they change their structure, they always expand. Naturally, each of the layers of the stars start to rotate at different angular frequencies. So naturally, you get shear inside the star. And if the shear is too much, little eddies can form and turn over and start to change elements between these. And so people have tried to implement this as good as we can in stellar evolutionary models. So let me show you the effect of that. So I think these are the results that got me into this field. So I saw these pictures in, so these are our models actually, but this is, it has been shown before in 87, is it 87? 89, André Meder had this in his models and proposed it for blue stragglers, but it has been forgotten. In 2005 it gained a lot of attention because people think these models could make long gamma ray bursts. We've been investigating this more, so this is from our grid. But this I just find astonishing, right? These stars, they move in the wrong direction in this diagram. Everyone knows stars expand when they evolve, but these guys don't. Eh? So lines of constant radius is roughly diagonal lines here. So big stars, small stars. These stars, they stay small and they only shrink during their life. So let me give you a bit of intuitive feeling, at least, for why this is happening. So we start again on the main sequence. You see there's a very small difference. These tracks for the fixed mass, this 40 solar, let's do the 30 solar mass. This star and this star, they almost start at the same position, not exactly. You see the rotating star is actually slightly cooler and less luminous. And so this is the simple part of the story. This is when the star has just one composition, it's just rotating, and the centrifugal support makes it a little bit bigger and a little bit cooler. But then as it starts evolving, you start burning helium into the center, hydrogen into helium into the center. And so you would like to build up this core, but it's mixed so well that in this cartoon picture you keep mixing helium throughout the star, and the star becomes slowly more and more helium rich. And so I guess it's easy to comprehend that helium is easier to compact in a small volume, right? So these stars just, they just shrink and become brighter. And so at this point, this little O here, that's the same point as on these tracks, this little point, this hook that we teach to our students. That's why the star has no more fuel in the center. That's happening in these stars as well. But now almost the entire star has been burned. And so the only thing the star can do is contract, what they do here. They contract all the way. This one is contracting all the way up to, there's not much light in here anymore. It's contracting all the way to this X symbol. And that's the moment when there's a tiny bit of hydrogen left still in the outer layers. It was mixed, but not fully mixed. It ignites. It has a very short moment of shell burning, so it has this hook feature. It's the same as when this star is trying to become a giant, but it only lasts very short. There's not enough hydrogen left, and it becomes extremely hot. And so we end up with very hot helium stars. So the interesting thing is that we find this mostly in lower metallicity environments, so stars that are more closely resembling the first stars in the universe. So I rescaled this. I showed you results for the metallicity of the Magellanic Clouds, for the small Magellanic Cloud, and I should emphasize that I gave you a really extreme rotation rate. I wanted to impress you with this, right? But if we would take less extreme rotations, the tracks would be pretty normal. So what I showed you should be very rare, and it should be happening in things that are SMC metallicity or lower. So at least 1/5 of solar or lower. You do see some effects, but it's still only happening for the very fastest rotators. This is for metallicities in our solar neighborhood, and you see all these tracks nicely go to the red. So either way, this has many interesting implications. So it has originally been proposed to make progenitors for gamma ray bursts. Because in one of the scenarios for this, in the collapsar model, you need a helium star that is very rapidly rotating It's very hard to do if you first have to become a giant. If you become a giant, you're big. It's easy to lose a lot of angular momentum because you have such a large lever arm. These stars, if they rotate, they only shrink and they stay small. And so this would be stars that probably still have a lot of angular momentum at the end of their lives and can probably drive an engine that can have a jet and that can get out of this star, and that we might see in a long gamma ray burst. Other many implications. These guys are very hot. Don't get fooled by how extremely hot they are. These are the surfaces of where what we call the end of the star. On top of that, there will be a stellar wind, so you might not get such crazy high temperatures, but these stars will produce a lot of ionizing photons. I don't have it in here, but we are just about to submit a paper with even lower metallicity, close to a nearby galaxy called 1 Zwicky 18, which is 1/30th of solar. And for those, we find such extreme events to be more common. And so the trouble is that these stars, they might mimic the presence of POP3 stars. So if you see, there's recent claims of, we see evidence for POP3 stars from the spectra. That's based on the fact that you need this really high ionizing budget. And these stars can mimic that. So it's going to be really hard to distinguish these guys from POP3 stars. And to be honest, these I presume they're more likely in the local universe, but you can decide on that. And then, well, on top of that, even at lower rotation rates, you will change the chemical yields of this. So that's. So keep in mind, these are models. We're talking about rapidly rotating stars, and we're trying to model those in one dimension, which is in principle not what you want to do, but we cannot do much better at the moment. And oh yeah, I'll discuss that in a moment. So we really do our best to test these models, but we don't have examples of these really extreme cases. But we can test them at slightly slower rotation rates. And so one of the main attempts to do this is to look and to observe the rotation rate of stars, or the projected rotation rate, and measure if you see strange elements at the surface that are not supposed to be there. And so one of the best diagnostics for us is nitrogen, because nitrogen is produced very early in the center of the star. When the star is hydrogen burning, it goes through CNO cycling, and nitrogen is enhanced, and it can travel throughout the whole star. And it happens that at least B-type stars, early B-type stars, have actually lines in the optical that you can measure. So I would love to. We have much better elements that we have predictions for, but it's kind of nice if there's lines that you can observe. So what would you expect? Rapid rotation. In principle, you would expect stars to be rapidly rotating to have more of the enrichments. That's how nitrogen works. So to be slightly better, if you have a sample with different ages, maybe you would expect this lower corner to be filled in, because young stars would be here and over time they would enrich. And to be honest, you needed to do it one step better. I will show you a comparison with the data set, but it had such a color cutoff that actually the young stars are cut out. So in a moment you'll see this band here, but that's because we mostly select stars that evolved. So in the moment you see in the color backgrounds, you see the predictions of the models, of a large grid of models that have been simulated as good as we can, how this diagram is populated and the data. So I don't know what you see, but it doesn't look so good, right? This is from the first VLT Flame survey. We learned a lot since then. And one of the things we learned a lot about is binary stars. And they mess up a lot. So let me first point out the problems, right? These stars are not supposed to be there, if models were right. There's all these slow rotators. But let me point out, this color scaling in the back is a logarithmic scaling. So your eyes are a bit fooled that it's pretty yellow over there, but the density of stars that are predicted there by the models are very low. These stars here, I don't know if you can see, it's very hard to measure nitrogen. So one of the big contributions of these measurements is, for the first time for so many stars, there was at least an attempt to measure nitrogen. But you see most of these are upper limits. Only some are actually measurements. But the upper limits are equally bad for the models, because upper limit means they're populating this part of the diagram where they're not supposed to be, right? So it's clear that this story is more complicated. So this either means that the models are wrong, or that we have to think about other things. And so we learned a lot about how to select your sample, and I will discuss that in a moment. There's probably a huge contribution in this diagram of binary products. And from nearby surveys, I will say less about that, but this is done in the Large Magellanic Cloud. If you do a similar survey in the galaxy, you can also measure the magnetic fields of these stars. And it turns out a lot of these guys are magnetic. We still don't know exactly what the role of binaries is, but we made the selection for this survey in such a way that it was, in retrospect, the most stupid thing we could do, and I'll show you that in a bit. So let's move to binaries. I said a lot about it in the talk yesterday, so I'll skip a few things a little bit. But so, if a massive star appears to be single, I mean, you have one and you really looked hard and you don't see evidence for binarity, and then you probably didn't look hard enough still yet, right? So there's probably another type of measurement. If you would go, if you would go in closer, you probably find some low mass companion. It's really hard to find an actual single star. There's a few where it has been really hard to find something, even when you do different methods and have a lot of observing time, different epochs, when the system is nearby. But still then, you have to consider this. So the single stars we see, there's a good chance that they're actually mergers of binaries, or that they were the second star in a binary system. You remember the runaway we talked about at the beginning, the fast-rotating star that's most likely came from a binary system and is now a single star, well, apart from that planet that the artist impression put it there. And you may think these are exotic things, and you can rule it out. And that's how the community, the massive star community, also has mostly done that. So if it's a single star, it was considered to be a single star, and this would be the exotic case, let's not worry about it. But that's not what we can do. So if you look hard enough, one of the persons that did this is Hugues Sana. He took data of over a decade and did a lot of effort to model the selection effects behind this. This is data of galactic nearby star clusters in which he followed up all the O-type stars and looked for binarity. And what you see is the distribution of period that he found for the systems that he detected and found solutions for. So it's a cumulative diagram. So each of these crosses is an observed system. There were 71 O-type star objects in this survey, and almost half of them had a detected, slightly more than half of them was detected as a binary system. And if you work out the selection effects, it should be more than half. So let me give you a bit of impression what this means, because it is we're plotting this on a log scale and a cumulative distribution. So if you would scale back an O star at birth to roughly the size of an apple, or roughly this size, this distribution means that at birth this star has a companion in 3 out of 10 cases, roughly at this distance, between this and this. Now you have a feeling how big an O star gets during its life. It starts as a couple of solar radii, and it can become well over 1,000 solar radii. So it would fill a good fraction of this room. 3 out of 10 has a companion this close, and either of them wants to be as big as this room. So that this means there's a good fraction of them that will do something to each other. It's very hard to imagine how they're not going to merge. And so in this diagram, 1,500 days, these are the very close ones. In 7 out of 10 cases, this other companion is still within the room, which means in 7 out of 10 cases they will interact. And these very close ones, probably many of them will merge. And so in the left diagram, everything is given in terms of a system fraction. If you convert this as fractions, what does it mean for massive stars, whether they're born? Because a massive star can be the primary or the secondary star in a binary. If we think about the fate of these stars, then only 30% of stars would be single according to this. And I should add that we are not sensitive to very low mass companions. We have very trouble to find extreme mass companions of more than a factor 10 with this particular survey. There are other techniques, and some people are working on that, finding very nice results. But these effectively single stars, they may still have low mass companions, and they may still have wide companions. So this is worrying, and so that led to this particular coverage in the mail. So this is partially for your entertainment, but mostly I want to make a point with this. Well, obviously this is not the point we want to make. Yes, it is a very exciting system, but here the system is portrayed as something very exotic. And so this is the switch that we have to make. Systems like that, the vampire systems, or let's just call them Rosslab overflowing systems, are not exotic systems. They are the main channel of evolution for massive stars. The main channel being more than half, 7 out of 10, will go through something like this. So they're not exotic, they're the mainstream class. And so that's what I wanted to show. So we try to model this, which is challenging. Binaries are much more complicated than single stars. I said a lot about that yesterday, but so this is the main challenge. For single stars, you can just make a grid of different masses. You want to do different compositions. And as I tried to argue in the first part of my talk, rotation needs to be considered. And this is where it starts for binaries. So we need to span this entire parameter space. So there's a good reason that the models are not out there, that you cannot grab them off the shelf. There's no models. We don't know how to do it. Well, it's not easy. And on top of that, we have a lot of extra physical uncertainties. And I'll stay a bit short because yesterday I discussed in more detail how we do this. But we try to combine detailed stellar evolution codes with codes that are really fast, that approximate the evolution of binary systems, that allows us to compute this. And credit for this is going to Rob Izzard, whose code I'm using. And so if you want to know more about this, we can talk later. But I'm going to show you results of this method. So I had 3 examples in mind. I probably don't have time for the third one, but we'll see how far I get. So how bad is it? There's many binaries, but let's say I observe, I have a galaxy, and I observe all the O-type stars, or all the O-type stars we can see from here, but it's a pretty random sample. So how many of them are binary products? That's the question you want to ask. If the question we try to do, we try to compare the data in our diagram. How many of these stars are polluted by being mergers and things that have gained mass? So this is what we try to work out. So let's start with a simulation where we start with these binary conditions that we derived for O-type stars. 30% are single, 70% are binaries. And these observations also give us how are the periods distributed, how are the mass ratios distributed. So we take that into account. So we let that evolve. And if you would do that for a typical galaxy, there's probably all kinds of populations that have different ages. So we do this for the case of continuous star formation. So that will give you different things, probably still single stars and binary stars and other crazy things. So what we find is there's still single stars that haven't done anything. I mean, there's stars that have just born there and there's stars that have evolved. There's still binaries that have not done anything, pre-interacting binaries. But then a good fraction of these are systems that are now transferring mass. Actually, a very small fraction. It's very hard to capture stars in this phase because it's a short-lasting phase. But the phase afterwards can be long. And so a good fraction in this particular simulation are stars that have gained mass and whose structure and rotation rate have been changed and maybe surface abundances. And there's a fraction of them are mergers. So there are many uncertainties in these models. So we don't believe these numbers by themselves. But we varied a lot of the assumptions in this simulation. So let me show you a table just to impress you. So there's different types of assumptions. Part of the assumptions come from the initial conditions, and part of them come from the physics treatment, how stars interact. And so we tried to identify the main ones, and we just varied them within the extremes that we thought were reasonable. And so these are the variations we find. So let me just summarize. So the mergers, you take a random sample of O-type stars in the galaxy. Let's say they have an age distribution which is roughly flat. Then 8 out of 100, 1 out of 10 is a merger product. And 3 out of 10 may be an interacting binary system. And there's pretty big error bars on there. We find variations that 8 can be 4 or almost 16. It's not completely fair because I have many uncertainties and I vary them one by one. So keep in mind that in principle nature can conspire against us and maybe all these knobs should be turned in one direction or the other direction. So the real error bars are bigger, but these error bars reflect the variations of the uncertainties, individual uncertainties. But it's the ballpark number. This is the model that we currently think is most representative. Maybe over time our understanding will change and these numbers will change a bit, but this is what we should be worried about at the moment. So 3 out of 10 early type stars in the galaxies are mass gainers and mergers. That ballpark number. So what does it mean for that diagram, right? So that diagram, we didn't take a random sample. We did something which was, in retrospect, not so smart. Well, there's a very good reason we did it. We took stars that look like single stars because we wanted to get rid of those binaries, right? And there's a good reason for that because if you have a binary, you have 2 lines, you have to disentangle them before you can do the spectral analysis. So there's a very practical reason to this as well. But the main reason was, let's throw out the binaries so we don't have this problem. So what happens if you throw out the binaries? So let me throw out the binaries. So we have all these products there. We have stars that gain mass. In some cases, they still have their companion, but the typical velocities, radial velocities you see of them are pretty small, maybe up to 30 kilometers a second. You have to capture them in the right moment. If you don't have really good multiple epochs, you will not throw them out. And some of them are single, so you will not throw them out. The semi-detached system, or this algal type system that are Rosslab overflowing, you will find those. They will show eclipses, and you will most likely see two lines. So that is the only ones you can easily take out. But that's such a minority of the things to worry about. The mergers, obviously, are not taken out if you throw out the binaries. They're now single stars. Or unless there was a triple companion, which is not unlikely, but it would not be too close. So, when you throw out the binaries, in this, here I'll show you the pie chart what happens. You throw out the binaries, we started with 3 out of 10 stars being a merger, being a product that you don't want in your sample, and it becomes 4 out of 10. So this is the wrong way to go. This is the remainder part of the sample. This is all the pre-interaction products. So this is kind of fun, right? This is a counterintuitive result. You want to get rid of the binaries, you throw them out, and you make the problem worse. And so that is a new way of approaching these data sets that we haven't fully appreciated in this community. And that's why we have to do this analysis again. And that's exactly why the second flame survey now has 6 epochs at once, right away. And we didn't select against binaries or in favor of binaries. We just have a magnitude cutoff, very systematic selection effect, so we can actually model this. And so the other part of it, if you want to test single stellar models, the best single stars are binaries, right? These are pre-interaction binaries. These are the stars you want to look at. The only way they have interacted maybe is tidal interaction, which changed the rotation a little bit, but we have some understanding of that. You're much safer interpreting the surface abundance of these than if you have a sample like that. So anyway, this is an ongoing process, so we'll learn. And hopefully the diagram becomes more clear. At the same time, we're trying to model how binaries populate a diagram. And that's exciting, but that's for some other talk in a few years maybe. Okay. Let's talk more about rotation rates, because rotation and binarity, that's just going together. A binary orbit has so much angular momentum. If you have one way to tap some of that angular momentum and bring it to one of the stars, you can spin them up a lot. So how to spin up stars in binaries? So the first one is in very close binaries. In very close binaries, the most favorable situation is that they keep facing each other, right? So the spin period of the binaries will be equal to the orbital period. And so that leads to very fun effects. So we talked about these first stars that go in the wrong direction in this diagram, right? The bluewards evolving stars. So our models predict you can do that in binary systems. So if you have a very close binary system, you also have, so in a typical binary system, if I use the same cartoons as before, stars would expand. We're talking about binary systems of a day or of maybe 2 days. And that's very close, so the star would expand and it would fill its Rosslab. That is the standard binary evolutionary scenario. But now we have these stars in these extremely short periods, 1.5 days, and here the stars are forced to rotate with 1.5 day period, which is very fast for such stars. And it means they are starting to move to the blue. So, so this is an HR diagram you see. This is not going to work better now, right? A little bit. So this is normal evolution. If it would not be a binary, it would have gone on to the red supergiant band eventually, but it was in a 4-day binary system. Here it filled the Rosslab. The 3.5 day filled the Rosslab here, 3 day, 2.5 day. At 2 days, you see the effects of mixing, and you see the stars bluer and more compact. 1.8 day, 1.7 day, you start to go with this blueward evolution. These particular models all came in contact. I stopped there. But we have models that go all this way and contract all that direction. And so this is very exciting. It needs to be explored further. But it would be very interesting to see if you can explain some of the extreme X-ray binaries. M33X7 or IC10X1, if you're familiar with those. The most massive one is a bit tough to do with the standard evolutionary models. This would be opening up a new window of evolution for this that was never considered before, because we didn't think about these mixing effects. And if this is a pathway to do that, this would also be a pathway to make 2 black holes in a system. And that's very interesting because they're very close already and they have a good chance of merging and possibly being detected in the next 2, 3, 4 years. This is a channel that is in none of the population synthesis code and the LIGO predictions. It's hypothetical, right? Because we don't know if this rotational mixing is actually working at the moment. But it's very exciting to think what these guys could do. There's more ways to spin up stars. One of the most efficient ways is to transfer a little bit of mass to the other star. And that's very efficient. If a star gains mass by a few percent only, it starts already to rotate at breakup. That's something also counterintuitive. It turns out stars have a real low moment of inertia. So you have a star, you give a little push, and it already starts to rotate at breakup. All the mass is in the center. You don't have to do much if the star gains 5% of mass on the equator from an accretion disk, it's at breakup. This is a problem in binary system because you don't normally accrete a few percent by mass. You can nearly double the mass of the companion. So one of the unsolved problems in this interaction physics is how much mass can the other one actually accrete. But it's clear you can spin them up. And so a third one of them, I put a question mark here, would be mergers. It's clear that if you have two stars in an orbit, the angular momentum that you have, if you would try to put it in one star, it would be beyond breakup. That's just impossible to put. I put a question mark because some of the hypotheses are that if you merge two stars, that you create so much shear that you might create little eddies which could drive some sort of dynamo. This has been proposed for merging white dwarfs, for example, last week, a nice paper on S2PH. There's no nice models for main sequence stars, but you have to keep in mind, if a merger leads to a large-scale magnetic field, these guys could actually spin down a lot. So these mergers are actually very interesting. I don't know if you still remember the diagram I showed you in the beginning. We had these strange, very nitrogen-rich stars that are magnetic and slowly rotating. So there would be a possibility there for mergers. Many ways to spin up stars. Tentative question, are all rapidly rotating stars actually coming from binaries? Can star formation actually make these rapid rotators? Or can we at least predict how many rapid rotators we make so we can take them out so then people doing star formation still know what they need to produce? It's already hard to make a star below breakup in the first place when it comes out of a cloud. There's a few orders of magnitude of too much angular momentum when you contract the cloud. So it's not helping that community, but it would be good to know if these fast rotators came from binaries. So we tried to simulate that. I'm going to show you a bit complicated diagram just to show you how diverse the evolution of binary systems is. So in each of these panels, I'm going to show you a different binary system, and each of them is going to show you how does this rotation rate, or the v sin I, sorry, the velocity at the equator change with the function of time. 4 different systems. 2 of them have equal masses. 2 of them have unequal masses. 2 of them are very short periods, and 2 of them are wider periods, just to show you different results. This is a pretty busy diagram, so the thick lines are the rotation rates of the stars. And the only point I want to make, there's a lot going on here, and it depends a lot what parameters you start with. And so you see a lot of effects here. So tidal interaction is one of the effects we take into account. And so in the bottom panel, you see the 2 shorter period systems, 2.5 days. It turned out I started my simulations with 100 kilometers a second, and 2.5 days turns out to be, it leads you to slightly faster rotation, especially as the star expands. So this rise you see in these 2 diagrams, that's because of tides. Then spin up by mass transfer. These crazy peaks you see here, that's the moments when the stars gain mass and they go to breakup. In this particular model, we have assumed they stayed at breakup. We have variations on that, but and then third, the merger. It's happening in the very tight system with a 20 solar mass star and a 5 solar mass companion. This unequal mass ratio makes mass transfer. It doesn't make it unstable, but the secondary doesn't know what to do with it, and it's engulfed, and it merges with this star. And in this particular simulation, we assume that mergers are fast rotating stars. You can do different simulations where they would be magnetic and spin down. So, that's a thought experiment. What if all stars are born as slow rotators? Let's define slow. This is a theorist experiment, right? So let's define slow as under 200 kilometers a second. It's a bit arbitrary, but under 200 kilometers a second, for the equatorial speed, we don't see many of the mixing effects. So let's start with a flat distribution, just the simplest we can assume. So I'm going to show you the result in the projected rotation rate. In the projected rotation rate, and the flat distribution in V turns out to be this distribution in the projected rotation rate. So you know what to compare with. This is the starting condition, and there's no star rotating faster than 200 kilometers a second in this simulation. And so we do the same simulation. We start with all binaries, let them evolve. For a population with continuous star formation, we get this diagram. So maybe let's focus at the thick line at the top. That's the overall distribution. There was no stars above 10 kilometers a second, 200 kilometers a second in the starting simulations, and all these stars have now been produced. This is all stars after rush lobe overflow. Here you see the contribution of the single stars and the pre-interaction binaries. They have changed a little bit. The pre-interaction binaries, they have changed a little bit by tides. You see some have spun up a tiny bit, but there's almost no change. The real part is the post-interaction systems. So let me, am I going to blow this up? Oh yeah. So let me blow this up. This is a combination, in this particular simulation, a combination of mergers and stars that have gained mass. And so these simulations tell you that, if you believe what we have done here, that 1 out of 5 massive stars in the galaxy is rapidly rotating because it had interaction with the binary companion. And so the error bars we find on that would be 20%, but the range is vary between 10 and 25%. That's the error bar to work with. So where we eventually want to go is to produce these rotation rates, go back and forth, and work out what is the real birth distribution of stars. And so this is sort of the game we want to play. We want to compare these distributions, On the left, I show you the distribution for the stars that are probably the B-type stars. It's just the binaries and the single stars. This is the O-type stars, we think. And we eventually want to compare with this. We only have the data for the single observed stars, so we cannot do the comparison yet. But one of the interesting features is we have this bimodality here. If we do model the selection effects, it will be very interesting to see if we can reproduce some of this. And if we can derive something about how much magnetic field would we need to do this. But that's for later. I think I can quickly do the third example, but then then I'll wrap up. So binaries do more things. They also change. I often get the question, how does it change the initial mass function? Well, binaries don't change the initial mass function. They evolve, and they can change the present-day mass function. But you can mess up a lot if you don't think about that and try to measure the present-day mass function. So there's many different ways to do this. If you are in nearby star clusters and you really try to count stars, you have to worry about this. If you look at a distant galaxy, you look at the integrated light, and you try to invert the initial mass function because you're tuning the knobs of starburst 99 to get things right, binaries will also have an effect. That's an effect that I'm not discussing here, but you can find papers from John Eldridge about that. Here we look at star clusters nearby that are very young, and where you have the stars are resolved so you can count them. So this is Fabian Schneider, was a PhD student in Bonn we worked with. He just moved on to a fellowship in Oxford, so he's doing very well. So this diagram is showing you, let's do first single stars for a moment to not lose you directly. So I'm showing you how many stars do we have per mass bin. So the dotted line is a salpeter IMF. That's what we start with. And then over time, so we went up to 100 solar masses, this is in log, 10 to the 2, 100 solar masses. Over time, these blue dots are for 3.5 million years. And over time, the first stars start to explode, so you lose them. And on top of that, these stars in this range, they lose mass, so they pile up at lower masses. So already with single stars, you change a lot in the present-day mass function. People are at least partially aware of this. I don't know how well the corrections have been done for this, but you get this funny bump for if you look at a young cluster, and a mass loss bump. And we think it would be very powerful to find this bump to actually find the real age of the cluster. If you go to later ages, it becomes hard to find this bump. But 4.8 million years, the mass loss, you're going to stars that don't have that much mass loss, so this pile-up effect is not so strong. So let's add binaries. This is the story with binaries. So binaries that merge, they have a second life. They can be rejuvenated. They're blue stragglers. These are the massive versions of blue stragglers. If you think about blue stragglers, people use the word blue stragglers for old clusters, where it's really clear which stars are blue stragglers. For massive stars, there's no nice turn-off of the cluster. So blue stragglers are probably merging with what you think is the turn-off. So it's very hard to distinguish them. But they probably sort of have a high mass tail. So there would be a couple of stars. And then the feature would be, so that's the binary tail from from mergers. So if you take just a couple of most massive stars, you get the age wrong of this cluster. It would be very nice if you could find this feature, this mass loss bump. And so we tried. We looked at arches and quintuplet. And I don't know if you find this so convincing. I'll leave that to you. But there's features in here. There's a lot in going to make this, how to make these diagrams and how the binning is done. And you could ask me a lot of hard questions that I will not have answers to. But we treated our models as close as we could to how the data is treated. So this is not exactly the same diagram. It has a funny binning shift. You can see that in this. The dotted line is still the salpeter slope, and you see this turn off here. That's the boundary effect. But what do you see here? There is a feature there. The blue dotted lines is our best fitting binary model to this cluster. If you believe that feature is our mass loss bump, then the age of arches becomes 3.5 million years. That's quite a bit older than, well, you know, it's all a few million years. It's all extremely young for most of you, I presume. But it is older than the previous estimates. For quintuplet, we find an age of 4.8 million years. Same story. And so this also means that the most massive. So if you believe this, it's yeah. So that would mean that the brightest stars in these star clusters are mergers and binary products. And so this is very nice because there's an outstanding age discrepancy between the brightest stars in arch and quintuplet and the stars below. It's very strange that these bright stars are there. So it actually makes it much easier to fit this cluster. The alternative with single stars is that the highest mass stars are younger than the rest of the cluster. You can evoke scenarios to do that, but I'll leave it to you to decide what you think is the easier solution here. Binaries are not easy, but it's you just with one age we can fit it. We added a lot of free parameters, so maybe it's not too fair to code for that, but we know binaries are there. This is also important if you think about deriving the upper stellar mass limit for how single stars are born. If the most massive stars in these clusters are binary products and mergers, then they're not telling you what is the most massive single star that can form. They're telling you what is the most massive binary that has merged and has not died yet. And so the stars I talked about earlier, the 300 solar mass stars, it's not at all clear that they are born as single stars or even single stars now. There's a good chance that they at least had one collision. And even it's so young, even for R136, our predictions are that's already a binary product. And so the third thing to worry about, well, if the brightest stars in binaries are binary products, then actually the radiative feedback and the ionizing mechanical feedback of these stars comes from binary products and not the stars described by a single stellar model. So that makes things very worrying. Good. I'm going to wrap up. Let me just say, there's a lot of exciting things that make the life of a star much more interesting or complicated, depending on how positive or negative you want to include this, to interpret this, than in the standard single stellar models. There's a lot of progress in the field where I came from, the massive star field, that has not all diverged to the other communities around that are using the stellar models. But I think it's good to be aware, even though we don't have the final answer yet, even though we don't have the final grids yet, you want to be aware of stars that do these kind of things before you infer that the IMF is flatter in certain galaxies. Well, anyway. Let me not rant at the last part of my talk. So I talked about two things. First part, we talked about rotation. This crazy hypothetical, for a moment, it's hypothesized chemical homogeneous evolution. It's a theoretical prediction. There's no foolproof. We have some indications that this might be happening. And most strongly from 1 Zwicky 18, this galaxy that has these special features that we can very nicely explain with these stars. But whether it's actually happening or not would be very exciting. It would be very exciting if this happens in binary systems, but because it's possible that the dominating black-hole merger channel comes from crazy things like this. But that's to be investigated. Second part, I think that's the part that is less hypothetical. The observations show is that a lot of these stars are in closed binaries, and there's no way around it. What the implications are, that is things we need to work on. But these things are in closed binaries, and they will interact. There's no way around that. So we looked at a few implications. We looked at rotation rates. Maybe all fast rotating stars come from binaries. Maybe if you take a random sample, you better be really careful whether you throw out the binaries or not, because it might be full of binary products that look like single stars. And if you want to test your single stellar models, you may want to use the binary models instead. The added advantage is you actually can get the masses from the orbits, etc. And we talked about implications for a stellar mass function of a star cluster. So Fabian Schneider proposes a new way to age date these clusters, if you can find this. Very nice. This is an example I didn't show you, but it also has effects on the ends of the life of massive stars and how they die as supernovae. So these directions, how does binarity change all these roles that massive stars have? Huh? We talked about there was cosmic engines and how we probe the universe. So I think this is directions that I'm very interested in to follow up with my group and that we're working on step by step with input from you and the community. But if you want to take away one thing, the rotation part is hypothetical, that's theory. The part I would put my bets on is this result. The large majority, I don't care whether it's 7 out of 10, If it was 4 out of 10, I don't think we would have made it into science if it was 4 out of 10. You know, there's something psychological about the majority, being 7 out of 10. But to be honest, the impact is comparable, right? So even if there is an error bar on this, this is something we need to consider. So thank you very much for your attention.
Thank you, Selma, for a very nice talk. Questions?
Were you trying to distinguish in models between binarity, mergers, and rotation? These all imply departures from spherical symmetry, and I would think that the polarization signature should be the most important signature you're studying. In other words, are you carrying along a polarization prediction with all these various modeling classes?
No. So the deviation of the symmetry is something to worry about, but it's in most of the cases we're relatively safe. And for the observational concept, so if your star is rotating up to 70% of breakup, it's very, very spherical. You would not see much. Polarization features, that is what people look at.
If however, it has an equatorial outflow, then you will see a very strong signal.
Yeah, true. There's an entire community, the BE star community, that is using this to probe the disk around these stars. Not my expertise, but that's heavily being used to probe this.
How does the formation of massive stars by mergers can affect the feedback amount and stuff like by wind and supernova?
That's a question. I have 2 PhD students working on aspects of that question. So the general trends, mergers can give star new life, and it can make them much more luminous. 2 stars of, say, 10 solar masses have certain winds and luminosities. If you add these stars together, it's not twice the luminosity, it's 4 or 8 times the luminosity. So these effects, they multiply in a very scary way, if you want.
Yeah,
now,
flux and stuff like that.
Yeah, not every star merges, but that maybe saves you a little bit. But there's other colleagues working on this as well. Impact on UV fluxes, for example, are I don't know all the numbers, but typical numbers. Clusters look maybe 20% younger if these effects are playing a role. So.
You glossed over mass loss in your evolutionary tracks. So what's the answer?
Yeah, so that's one of the big debates in the field that people are looking into. It's very hard to compare the theoretical predictions with the. Well, it's very easy to compare the theoretical predictions with the observations. The big question is: are the winds clumped for at least the winds of hot stars? That leads to a certainty of 3 to factor 10. What we really need is UV spectroscopy. So if some of you are in the panel. This is our treasury proposal to get UV spectroscopy. It's exactly to get these winds of massive stars right. For me, I didn't focus on this because since I work on binaries, if you strip out mass on a binary, it's almost negligible what the stellar wind is doing compared to what the companion is doing. So this is not the main thing I personally focus on, but it doesn't mean it's an unimportant issue.
I like your 2 dancers doing the pas de deux. But how about pas de trois? What's the role of triples? Or have you gotten that far?
No, yes. Well, I'm not modeling them directly. There's a couple of people in the field that have, I'm advocating for binaries throughout, and we can have similar talks like that. In the observations I showed you, I'm involved in, but I don't do the observations myself. But all these short period systems, this 3 out of 10 that are like this, nearly all of them probably have a companion, a third one. Yeah. But it's probably either just within this room or outside. If it's within the room, it's going to be a lot of fun because these guys can merge, and during the process of swelling up, it might already do something with the third star. So there's a lot of that's a whole nother Pandora box. So it's it would typically affect maybe at best 20% of the stars. So let me first solve the 70% of the stars that are binaries.
But might it be involved in the runaway stars?
That's very possible, especially in star clusters. Having multiple systems like this, you need triples. I think the most important thing for the LIGO predictions, the gravitational wave predictions, you need very rare channels, and having a triple companion can help you probably a lot better. But that no one has explored that quantitatively in a thorough way.
You mentioned briefly the role of these rapidly rotating stars in reionization. So, first of all, what fraction of stars are actually so rapidly rotating? Is it large enough that they could be important for ionization? And secondly, your models are presumably of the current stars that we see, but the stars doing reionization would be POP3 stars, which are quite different. So do you think those conclusions actually can be?
So with rotation, not only the POP3 stars could be contributing to reionization, but also stars that have some metals. With 1/30 of solar and fast rotation, you could contribute significantly to it. In the nearby galaxies, in the Magellanic Clouds, and what we see, at best in our survey of 1,000 stars, there might be one star partially going along this track. And then according to the IMF, it's not going to be the most massive one. So for the large Magellanic Clouds, one of these guys will impact the ionizing budget for that region, but maybe not. I think for the reionization, it's much more interesting to think about the binaries, because they can make ionizing photons much later in their life, which is very interesting, because you don't just want to make the photons. It would be kind of nice if they also escape the star-forming region, right? So, anyway, there are things that will come out at some point.
You made the comment that you could do several models a day. You actually should be doing take several months per model and be doing three-dimensional.
That would have been a different career choice, and there's a few.
You can make your graduate students do the work.
Yeah. There's a few groups that are doing this. Jan Fay, what's his name? We have an Einstein fellow here who is not doing the full star in 3D, but he takes a box, just takes a surface of a little bit of the dynamical time scale of a massive star. These amazing simulations of the radiation transport in one of the outer convection zones that we don't understand. So there's a lot of people working on this. I like to understand these things as a whole. It's very fun to switch from individual systems to an entire population. There's entire new behavior of how the population behaves, apart from the physical laws for population that are ending up with different results. So I enjoy this area a lot. But you're right, this is a very important part to do.
So Selma, with all these binaries and being massive stars and very large, the whole role of common envelope evolution of these things, whether they merge or whether they don't merge, is a big question. As you know, that whole common envelope track is remarkably uncertain. So what effect that has on trying to understand these larger questions?
The larger questions.
I mean, the role of common envelope evolution.
So there's many large questions. Maybe for common envelope, I think the most interesting questions are: can we make double neutron stars and double white dwarfs? Right? It's clear that you need you need two common envelope stars. Also, there for the common envelope, that would be a stronger point for the point you just made for 3D models. I think there's no way that in the type of models I have, that would be zero dimensional. We're just going to do an energy budget. That's all. So you have some people in the room here. Morgan is one of the people trying, has nice papers on this, on improving there. And, you can summarize the state of the field better, but I don't think any of the models has even managed to eject the common envelope.
No, that's right.
So,
it must be just a major part of the story. I'm just wondering.
So in a way, for me, this is arguing also to not only do 3D models, but also do this, because at least I can explore what happens under extreme variations of the assumptions that Morgan will need a few more PhDs to, and a few supercomputers to start to explore a few more models.
But that's the problem with the 3D models, is on the dynamical timescale for which you can do these calculations, it's not long enough to eject, have everything ejected. You're not done. You have to then map it back to a 1D calculator or something. You have to go to implicit. So.
All right. Thank you very much, Selma.